Welcome and thank you for joining us for today's webcast, A Product Engineer's Guide to Specifying the Right Coating, sponsored by Boyd Coatings Research Company and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speaker. Don Garcia is a coatings expert with more than 30 years of hands-on technical experience in literally every facet of the coatings business, from spray applicator to president of the Boyd Coatings Research Company. Areas of specialty range from aerospace and medical to military and high reliability, high performance coatings. Boyd's coatings are used in applications from the ocean's bottom to the high reaches of outer space and everything in between, with complexity ranging from simple aesthetic showroom finishes to complex technical rocket engine matrices. So at this time, I'd like to hand the program over to Don Garcia.
Thank you, Billy, and thank you all for attending today. We appreciate your attendance. Let's get started. So why use a coating is a question that we're going to ask, and to protect parts from damaging environments, to impart corrosion resistance, chemical resistance, abrasion resistance, or to change the properties of a surface. So wherever we want to protect a surface or change the properties of a surface, we can employ a coating. We might want to make it non-stick, or lower its coefficient of friction, make it inert, meaning non-reactive or biocompatible. We may need to make it conductive, so we may have a non-conductive surface that we want to make conductive by use of a coating. We can make it electrically insulating, so we can take a metal, for an example, put a coating on it that will then insulate it against some electrical current. We may simply want to change its appearance. We may want to make it look different than what it is, make it look better, or perhaps use it to identify, as is the case with these items that you see here. That identification not only adds the identification, but gives you a corrosion-resistant, high-performance finish that can survive adverse environments. Here we're looking at a short list of popular coatings, coatings that are available and coatings that you're probably familiar with. We're going to talk about some of these coatings as standalone materials, and we're also going to talk about them in combination with one another to impart the properties of each into a combination or hybrid coating. We're going to focus on three commonly used groups today, given that we have a fairly short time together. So we're going to look at coatings with electrical properties, fluoropolymers in general, and hybrid coatings. Hybrids being combinations of different polymers and different materials to get the best of all of those properties. So in the electrical coatings, we may want to impart EMI or RFI shielding. We can do that by adding to different resins fillers. Those fillers can be silver, copper, or other metals that impart a property to a resin that give us a finish that produces this type of shielding. They produce conformal coatings that can be selectively applied to surfaces or applied to entire surfaces. An example of that would be an endoscopy device, such as a camera housing, where an EMI RFI shielding might be required to eliminate electrical interference. But we may also want to impart electrical resistance or non-conductivity, and we can do that on the same item with two different coatings to impart two different properties selectively. As we go through the presentation, we're going to talk about the pros and cons of these different types of coatings, where we might use them and where we might not want to use them. So in the EMI and RFI shielding, Coatings are easier than plating to apply selectively, which makes them better. They can offer greater performance properties because we can vary the resins that are used in combination with the metals to give us those high-performance properties. And typically, they're less expensive than vapor or vacuum deposition. Some of the cons are somewhat higher cost than plating. We move on now to fluoropolymers, and these are fluoropolymers that we're going to discuss. This list is by no means all of them, but the most common types. So we've chosen these 6. So fluoropolymers can offer non-stick, low coefficient of friction, non-wetting, heat resistance, unique electrical properties, cryogenic stability, chemical resistance, and biocompatibility. So fluoropolymers have properties that one can specify or one can look to give us very high performance on various substrates. It is relatively expensive, or they are relatively expensive as compared to other finishes. But generally speaking, they are very high performance. So I want to talk a little bit about Teflon. It's a trademark that's commonly used, very well known, but occasionally will be specified as a material. So someone will say, we want a Teflon coating. This is a generic and not an exact material, so it's a trademark or a brand name. So when specifying materials, we want to make sure that we specify the coating itself and not necessarily a brand name. There are other brands with similar properties as Teflon and other properties. So really, the specifier needs to look at the properties of the coating and, more importantly, look at the application. So if you were to call Boyd Coatings and ask for a Teflon coating, the first question that we would ask is, what do you expect this coating to do for you? Where is it that you're going to use it, and what properties are you looking for? So we can then drill down to the exact material that's going to serve the purpose. So each fluoropolymer has trade-offs, pros and cons again, and we're going to review that in the following slides. So PTFE has low coefficient of friction, extremely low coefficient of friction, is a non-stick material that is inert with very high operating temperature, or relatively high operating temperature, good abrasion resistance, and a long history in medical and aerospace uses. So it's something that is well known in the industry. An example of where PTFE might be used is in guide wires, medical guide wires, to impart lubricity while still being biocompatible, and other properties are imparted. Material is, however, inherently porous. So although the polymer itself is resistant to chemistries and is a very good polymer, it is, as a coating, inherently porous, so we would not specify that in areas where chemical resistance or other need for an impervious surface is required. And also, the substrate that's to be coated has to endure the elevated cure temperature that's required, somewhere in the 700 to 800 degree Fahrenheit range. This is a recurring theme that's going to be throughout the presentation, talking about enduring elevated cure temperatures. And really what we're trying to tell you is that we need to look at the substrate and how it is going to be compatible with the coating and the coating application process. Furthermore, we look at downstream operations that might be conducted on the components to make sure that the coating is going to survive those downstream operations. Another fluoropolymer, FEP. FEP also has very low coefficient of friction, is a non-porous material. So as opposed to PTFE, it is a thermoplastic that is non-porous and would serve well in areas of chemical resistance and impervious or less porous applications. It's a non-stick material that has very good chemical resistance and good dielectric strength. Dielectric strength is something that we have to take into consideration as a theoretical number. So if you look up the dielectric strength of FEP or any of these fluoropolymers, it's going to give you a value. That value is theoretical. Doesn't necessarily mean that if we apply 1 mil of FEP that we'll necessarily get dielectric standoff of 1300 volts, but it is a guideline. FEP can also be used as a bonding agent, where it's interesting to note that although these are non-stick materials, the thermoplastic fluoropolymers, if remelted or recured, can actually be used as glue. They will bond themselves to each other as well as to other substrates, so that laminations can be made with these high-performance materials. It is a fairly soft material, so we wouldn't apply it in areas where abrasion resistance is required. And it does have lower operating temperature of 400 degrees, and again, has to survive high cure temperature of 700. PFA is another fluoropolymer with excellent properties. Has low coefficient of friction, although it's a little bit higher than that of FEP, and PTFE still imparts low coefficient of friction, while also giving us a very tough and durable finish. It's able to build in thick films, which can be useful if permeation is an issue, because the thicker that we can make a coating, the longer it would take for a chemistry or whatever the environment is to permeate through these thicker films. Has excellent dielectric strength, is a non-stick, inert finish with high operating temperature. It's difficult to apply in thin films, so if there were a specification that required tight tolerances or very thin films, this would not be a good choice. And again, high cure temperature required for this coating. So here what we get is the low coefficient of friction, chemical resistance of the other polymers that we've talked about, but now we get it in a much thicker film that is much more durable and able to take abrasion and applications where toughness is going to be important. PVDF is a material that's used very commonly in instruments, medical device instruments, with a good chemical resistance, a durable finish that is inert and is available in many colors. So this is a material that can be used not only as a performance material, but also enhances the appearance of a device or an item. If color is important or if appearance is important, this provides that along with performance. It has good dielectric strength, lower cure temperature, and has a long history in reusable medical devices where sterilization requirements require a coating that has very high performance and also stands up to the rigors of being handled on a daily basis. It has a lower operating temperature, so we wouldn't want to put this coating into an environment that has a high operating temperature, and higher coefficient of friction, so we wouldn't necessarily specify this if lowering the coefficient of friction was the main characteristic that we were looking for. ETFE and ECTFE are materials that have excellent chemical resistance, very good durability. They're able to build in very thick films and have good dielectric strength. So these are materials that we would specify in vessels or tanks containing very aggressive solvents, or anywhere where a chemistry can attack a surface, and we're really not looking for the other performance characteristics, be it low coefficient of friction or electrical properties necessarily, but really want a good chemically resistant coating. Difficult to apply in thin films, And higher coefficient of friction, as I've said, make it a good choice in some applications, but certainly not all. Now let's talk a little bit about hybrid coatings. These are coatings that combine the properties of two or more to achieve a balance in performance. Some of these include, but by no means is this the limit of what one can do, PPS, PTFE, polyphenylene sulfide with polytetrafluoroethylene, PES, polyether sulfone with PTFE, FEP with an epoxy, FEP with amide-imide, or PTFE, TFA. There are many others, but we're going to talk about these because these have some properties that are unique. So examples, combining the low coefficient of friction of PTFE with either PPS or PES and its durability can achieve a tougher non-stick lubricious coating. Essentially, you get the properties of both. So, for an example, PES is very good in terms of its ability to be impervious to water, to boiling water. It's used to make coffee makers, things of that nature. When it's added to PTFE, you get an impervious, low coefficient of friction coating. PPS, PTFE, has the chemical resistance of both of those materials, the PPS and PTFE, is non-porous, unlike PTFE alone. And since PPS is a very hard material, it gives you the added hardness or durability that could be used on things like lead screws, gears, areas where low coefficient of friction of PTFE alone might not withstand the abrasion and the rigors that those components are put through. It's not as flexible, so its hardness gives it some rigidity that makes it non-flexible, so we wouldn't want to put it into an application where flexibility is a requirement. And again, we have the high temperature curing of 700 degrees Fahrenheit. I'd like to say at this point that we will have time for questions and answers, so I hope that there will be some questions at the end. PES, PTFE. So PES, as I mentioned, being impervious to water and non-porous, gives us a surface that is flexible. So now we can use this combination in areas where flexibility might be something that is desirable. It can only be applied in thin films. It doesn't like to build up thick and has the high operating temperature or cure temperature that's required. So an example of where we might use something like this is in a water valve, a valve that has sealing surfaces where we want the corrosion resistance or impervious to water characteristics that PES provide, along with the non-stick and lubricity of PTFE, so when these valves operate, or if they sit for long periods of time, we get them to release and the sealing surfaces aren't damaged so that they can seal once again when they're closed. FEP epoxy is another combination that can be used, and this provides chemical resistance along with durability, good non-stick properties, and lower cure temperature. So now we have a combination of materials that will give us a wide range of properties, all of which are good, none of which are really the highest performance, but it's a good all-around material that opens up other components that can be coated because their cure temperature is lower. These are, however, not resistant to strong acids and have lower operating temperatures, so that, again, all of these factors have to be taken into consideration when we're specifying these types of materials. FEP amide-imide is another combination that can be used where durability, good non-stick, and a bit higher operating temperature is required. So if the substrates can withstand those higher temperatures, we can bump up to a higher level of performance. But these are generally good all-around coatings that can be used where not one single property is of the utmost importance, but we want a well-rounded coating that gives us different properties, all of which can be combined. Again, not resistant to certain acidic conditions and is a fairly high temperature at 600 to 700 degrees curing. PTFE PFA is an excellent non-stick material that is extremely lubricious and very durable. It is, however, a thin film. So although a material may be durable or hard, its thickness or its toughness come into play, because even though it's very hard, if it's very thin and comes in contact with some other metallic surface, it might easily be scratched off the surface and therefore render it useless. It is a relatively expensive material, given that it's a three-layer system that combines not only the PTFE and PFA, but also has some other ceramics, mica, materials that are in there to give it higher durability. PTFE polyurethane is an interesting material. This is one that we developed as an air dry coating so that it can be used on virtually any substrate. It can be applied in the field. It doesn't necessarily have to be applied in a controlled environment. It has outstanding hydrophobicity. This is used in applications for Kevlar and other low-temperature substrates that cannot withstand high-temperature curing, where hydrophobicity is required so that water doesn't interfere with a signal given by this installation. It is not biocompatible, however, so although it has excellent properties, its non-biocompatibility would limit where it could be used. So generally speaking, hybrid modifications are suited to an application. We can adjust the constituents of a material to optimize the properties. So we can put less fluoropolymer into a material, which makes it cure at a lower temperature. We can add ceramics and other materials to improve its abrasion resistance. Every material and every application has performance trade-offs. This is where the specification and the specifier have to take into consideration all of the different variables that come into play when choosing the right coating. We can help you combine those. We would appreciate an opportunity to do that. And in summary, there are many types of coating available, each of which can provide unique properties. And as I've said, many factors have to be considered when selecting a coating to ensure maximum performance. And it's always best to consult a professional before specifying a finish to make sure that all of these factors are taken into consideration. So I'd like to thank you all for your attendance and for any questions that are going to come. Feel free to email me directly to look at our website. We'd be happy to answer any questions that you might have, and I'll turn it back over to Billy.
Thanks, Don. At this time, we'd like to begin our Q&A. Those questions not addressed during this webcast will be addressed at a later time by a member of the Boyd Coatings team. We have plenty of questions here. This first question, Don, will be a good opportunity to elaborate on surface preparations. Is anodizing a good alternative to sandblasting as a surface preparation for powder coating aluminum?
It can be. The issue with anodizing is that if the plater seals the surface, then you have a surface upon which these coatings don't necessarily like to adhere. So sandblasting a surface basically cleans it and improves its surface condition, but also gives much more surface area by virtue of having peaks and valleys in the surface that give you greater adhesion. But anodizing is and has been an alternative, but we would caution you not to seal the surface.
What range in maximum temperature resistance would one expect for an organic-based coating?
So most organic-based coatings are in the 250 to 300 degree range. These fluoropolymers like PTFE can get as high as 550 degrees Fahrenheit, but anything in excess of 550 is beyond the capability of these types of finishes.
Here's another question from one of our attendees. Would you comment on the environmental impact aspects of fluoropolymer coatings in both material preparation and in industrial coating processes?
Well, obviously, these materials can have an impact on the environment, and one has to be very cognizant of that. One has to have the proper equipment, the proper protective equipment, not only for the environment, but for those people working with these materials. So by no means are these materials that should be handled, used by anyone that is not a professional, that hasn't gone through the training required, and also has the appropriate permitting to make sure that we safeguard the environment.
Are these hybrid fluoropolymer coatings applied via powder coating, liquid spray, or some other method?
All of the above. So the materials themselves, so we on occasion will get a client that calls and says, we'd like to have something powder coated. So as I mentioned before, Teflon is a trademark. There's also application methods that someone might use as a specification to have something powder coated. This is just a means of conveying the material to a surface. So for an example, PFA that we spoke about is a material that is available as a powder and also as a liquid. So it can be sprayed as a dispersion, it can be sprayed as a powder, it can be sprayed electrostatically, conventionally, it can also be dipped. So there are many methods, and that is part of the specification process that we go through based on the component's geometry, cost considerations, transfer efficiency, and other factors.
Can any of these coatings be used on elastomers?
Some can. They have to be lower temperature, for the most part, lower temperature curing materials. Depending on the temperature resistance of the elastomers, for an example, PTFE might be used, although we might not fully sinter it at the 700 degree Fahrenheit range. We might sinter it at a lower temperature or leave it as a sacrificial surface that doesn't get cured to the extent that a fully sintered material would.
We have time for a few more questions here. Is there an optimum coating thickness for each type of coating or a generalized rule of thumb according to the substrate or application? Hard to generalize in terms of thickness, but there are materials, as I mentioned in the presentation, that do not apply well in thick films and conversely do not apply well in thin films. This really is driven by the material itself and its inherent nature, its particle size, whether or not it's a thermoplastic or a thermoset. So there isn't really a rule of thumb per se, but there are certain limits to these materials. What disqualifies a coating from being biocompatible?
Well, generally speaking, anything that is going to have an adverse effect on a human being would be non-biocompatible. So, for an example, if heavy metals were present in a coating, that would probably disqualify it as biocompatible. If other materials are present that are known to cause irritation or some other persistent problem, that would disqualify them.
Okay, this will be our last question since we're running out of time. What types of substrates can be used with these coatings?
The substrates can be varied and diverse. Really, it's a matter of choosing the right coating to apply to the substrate that gives you the performance. So the trade-offs that we talked about come into play with substrates as well. A piece of wood could be coated. However, the type of coating the one might apply there is limited, so its performance might be limited. Noble metals, all kinds of different substrates can be coated, and it's just a matter of the right preparation, the right sequencing, and choosing the right coating. And that's where we hope to be of service.
Okay, thanks, Don. Great presentation.
Thank you.
That concludes today's webcast. Thanks to everyone for joining us. Again, those questions not addressed during this webcast will be addressed at a later time by a member of the Boyd Coatings team. Just a reminder, this webcast will also be available on demand at www.techbriefs.com for the next 12 months. great day.